Okay, so last time we started with this graph theory module. So again, for people who are new to graph and everything and who are not here last time, so basically what a graph is a set of nodes and edges. Uh, so anything in real world could be modeled as a graph. So let us say we have a network of 4 computers. I could model that as a graph with each computer as a node, and a link between the 2 computers is called an edge. So we interchangeably use this terminology. A network in this course is basically a graph. A node can be called as a vertex, a link is an edge. Now any of these 3 real world networks could be modeled as this graph because they have the same structure. So let us say you have the actor network. So these are the 4 actors, and there's a link between 2 actors if they have at least acted in one common movie, and this is such actor network, and we could model each actor to be a node and capture those links as edges. Similarly, this is a protein-protein interaction network. So each is a protein complex, and there's a link between 2 proteins if or protein complexes if there's some interaction between them. So those links can be also captured as edges, and those 4 protein complexes are the nodes. So even though they look like 3 different physical networks, you could model them as a graph, and you see the graph structure is the same. So you could then run some graph theory algorithms, as we'll do in this course, on these graphs and find out some properties and characteristics of those graphs, and decide those are the characteristics you can also expect in those real world networks. Okay. So one thing that we will need to know is how to store the graph information. So a graph could be stored as an adjacency list. Okay, still somebody's missing. Okay, so a graph can be stored as an adjacency list. Now before that, also we can have directions for the edges or no directions for the edges. If there are no directions for the edges, it's called an undirected graph. An undirected graph is essentially the edges can be used in both directions, to communicate in both directions. Whereas in a directed graph, you have edges with direction. So if you think like a communication network, there can be information sent only from 1 to 4, not from 4 to 1, because the edge direction is from only from 1 to 4. Whereas here, there's no direction, so you can basically send in both directions. Or it's like, think about road. This is like a one-way road from 1 to 4. This is like in both ways you can go from 1 to 4. So we use what is called an adjacency list or an adjacency matrix to represent a graph. Either one of them is good enough. So an adjacency list is kind of like an array of linked lists where you can have the node IDs, and for each node ID you have a list of what are called the neighbors of those vertices or nodes. So for example, for node 1, so the neighbors means those who are adjacent or next to it. So for node 1, it has an edge to 5, 3 and 4. So we say 3, 4, 5 are the neighbors of 1. So we can write them in any order, doesn't matter, it's just like we write in the increasing order of the node IDs. Then for 2, 4 and 5 are the neighbors, and so on. Now for now also the number of neighbors of a vertex is also called the degree of a vertex. So we saw this terminology in detail last time. So the degree of a vertex is the number of neighbors of the vertex. So for example, in this graph for node 4, 1, 2, 3, 4, 5, there are 5 neighbors for node 4. So that's the degree of that vertex. So I encourage you to go through this portion on the degree. And then the adjacency matrix is a binary matrix, it's a square matrix. Now for an undirected graph, it's going to be a symmetric matrix. So let us see what first an adjacency matrix represents. So if there's an edge, say in this case between 1 and 4, then the entry for row 1 column 4 will be 1. Similarly, the entry for column 1 row 4 will be 1 because it's in both directions. So basically you look at the row ID and column ID and put a 1 in that cell. If there's no edge, say between 1 and 2 there's no edge, then for row 1 column 2 there is no edge, so entry is a 0. Now it's a symmetric matrix. As I said, if there's no edge from 1 to 2, there's no edge from 2 to 1 either. So the entry for row 2 column 1 is also 0. So that means the row entries for node 1 will be same as the column entries for node 1. So 0, 0, 1, 1, 1 is the row entries. Similarly, 0, 0, 1, 1, 1 is a sequence of column entries for node 1. For node 2, the sequence of row entries is 0, 0, 0, 1, 1. Similarly, it is 0, 0, 0, 1, 1 for node 2. For node 3, it is 1, 0, 0, 1, 0, 1, 0, 0, 1, 0. So you could expect this property in undirected graphs for adjacency matrix. For directed graphs, you cannot expect this because the edges can be in only one direction. So you, again, for directed graph, you follow a convention. I'll represent the edges going out of a vertex. Okay, so outgoing neighbors, that's what you can call, or outgoing edges. So in the case of adjacency list, for node 1, the outgoing edges going out of node 1 are 3 and 4. So that's what you capture here. For node 1, its outgoing neighbors are 3 and 4. One has an incoming edge from 5, and you don't need to capture that for node 1. That will be captured for node 5. For node 5, its outgoing neighbors are 1 and 2. So that's how we represent it. For node 2, there are no outgoing neighbors. For node 3, no outgoing neighbors. For node 4, the outgoing neighbors are 2 and 3. Similarly, in the adjacency matrix, you capture the outgoing neighbors. So if there's an outgoing edge from 1 to 3, so row 1, column 3, you have a 1. There is an outgoing edge from 1 to 4, row 1, column 4. This edge from 5 to 1 will be captured in row 5, column 1. So from which vertex the edge is originating or starting, that's the row vertex, and where it is ending up, that's the column vertex. That's the convention we will follow. So 4 to 2, 4 is the starting vertex, to 2, so there's an 1. So that's the adjacency matrix representation of a graph. Okay. Then we had degree, so it's quite easy to follow through. Just go through the exam. Okay, let me go quickly. So how to get the degree distribution of the vertices? So given a graph, find the degrees. We should know by now just the number of neighbors for each vertex. For node 1, the degree is 3. For node 2, the degree is also 3. For node 3, the degree is 2. For node 4, the degree is 5, and so on. So once you get the degree of the vertices, find the range of values among the degrees. So you have 2, 3, 4 and 5 are the different degree values you could see for the vertices. So now write down all those different degree values you have in the graph, and then for each degree value count the number of nodes that have that specific degree. So how many nodes have degree 2? There are 3 nodes that have degree 2. How many have degree 3? There are 3 nodes with degree 3. There's only 1 node with degree 4. There's only 1 node with degree 5. So once you get the count of the number of nodes, you can add up the number of nodes and you will see that the total is equal to the number of vertices in the graph. So if you add this count, 3 plus 3 plus 1 plus 1, there is 8. That's the total number of nodes in the graph, 8 vertices. So then what you want to find is the probability of finding a node with a particular degree. So for that, you just divide these numbers for the degree by the total number of nodes. So you have 3 nodes with degree 2, so divide 3 divided by 8, that's going to be 0.375. Again, this 3 divided by 8 is 0.375. 1 divided by 8 is 0.125, and so on. So what this probability means is, so given a graph, given this particular graph, if I randomly pick a vertex out of that graph, what is the probability that the vertex that I pick will have, say, a degree 2? That is, this probability 0.375. So you think, look up at this graph, there's no vertex with degree 1. So that means if I randomly pick a vertex from this graph, what is the probability that the vertex I pick will have a degree 1? That is 0, because there's no vertex in this graph with degree 1. So for degree values that are not listed here, the probability is 0, and that corresponds to what I just explained. So these numbers indicate what is the probability of finding a vertex with a certain degree in this graph, and their probability values should add up to 1, because you see you divided these numbers by the total number of nodes, so the sum of these numbers also is the total number of nodes, so the probability values should add up to 1. And now how to find the average degree of a graph? So 3 ways you can find the average degree of a graph. One is to just sum up all the degree values and divide by the total number of vertices. That's the typical way we find average of numbers. So in this case, these are the degree values of the vertices, so just sum up the degree values and divide them by the total number of vertices. So in this case, you will get 3.0. Now another way you can get the average degree is using this probability values. So from a statistics or a math class, you should have come across this formula. Given the different values a distribution can take and the probability of observing those particular values, the average of those values can be determined using this formula. It is sigma k equals 0 to infinity. That means basically the different values of, so k is now here the degree. So different degree values that you can observe in the graph. So k times pk, that is the probability of finding nodes with a certain degree. Now here the degree values are 2, 3, 4, 5. So basically multiply 2 times this point 0.375 plus 3 times 0.375 plus 4 times 0.125 plus 5 times 0.125. So that should also come out to be the same number 3 that we got with the first approach of just summing up the degree values and dividing by total number of nodes. Now there's a third approach that I also went through last time. So if we add up all the degree values of the vertices, the sum of all the degree values of the vertices will, and this is undirected graph, so sum of the degree values of the vertices in an undirected graph is going to give you twice the number of links. That's because when you add the degrees, so if I add the degree of 1, which is 3, I'm considering each of these edges attached to 1 once. And then when I can add up the degree of the other end vertex, so there's a terminology called end vertex for the edges. Basically 1 and 7 are the end vertices of this edge 1, 7. 1, 3 are the end vertices of the edge 1, 3. So when you add up the degrees of the end vertices, you're considering each edge twice, once for each of those end vertices. So when I add the degree of 1, I'm considering this edge 1, 7 once. When I add the degree of 7, I'm considering the edge again. So that is why the sum of the node degrees will give you twice the number of edges. So you can then, so that is the relationship. So you can then divide that sum of the degrees by 2, because sum of the degrees is twice the number of edges. So divide that sum by 2, that will get you the number of links in the graph. So that is one relationship. The other relationship is, again, the first approach I explained, the sum of the node degrees divided by the number of vertices should get you the average degree. Now if you put together these two expressions, the sum of the node degrees is a common term in both these expressions, and from this expression the sum of the node degrees is like simple cross multiplication, 2 times the number of links, and you can replace this with 2 times the number of links in the numerator divided by the number of nodes. So this is another way you can calculate the average degree of a graph. It is simply twice the number of links in the graph divided by the number of nodes. Now this relationship also indicates one important characteristic of a graph, that to find the average degree of a graph, you don't really need to be given a graph, because as you can see in this formula, the average degree is 2 times the number of links divided by the number of nodes. So all you need is the number of nodes and the number of links in the graph, and you can get the average degree. Of course, I'm not interested in the individual degrees or for the particular vertices. What I want is the average degree. So that means I could give you some graph with a certain number of nodes and certain number of links, and I can specify whether it's an undirected or directed graph. For undirected graph, the relationship is twice the number of links by the number of nodes. For directed graph, it is simply the number of links by the number of nodes. So using this relationship, you can find the average degree of a graph without being given the graph itself. Okay, and still you should get the same number, 3, in this example here. So the 3 ways, and you should be familiar with all the 3 ways to find the average degree, right? So this is basically what we went through. And last thing we went through last time was Assortativity Index. Let's see. Okay, so the Assortativity Index is a measure of how similar are the end vertices in a graph with respect to degree. So for example, given this graph and the edges in this graph, if I considering all the edges in the graph, or the end vertices of the edges having similar degree or different degrees. Okay, so if the end vertices of the graph have similar degrees, then the graph is said to be assortative in nature. Okay, you can extend this to other properties too. So given a social network, so think about this as a social network, and instead of considering degree, you consider, say, the ages of the people in that network. And for every edge, the 2 people at the end of the 2 edges have similar age, means comparable age, then the network is said to be assortative. On the other hand, if the 2 people at the 2 ends of the edges have different degrees, so young people connected with old people and so on, then the network is said to be disortative in nature. So it is the ends of the edges that are used to calculate the assortativity index. So we are going to go through again the calculations today in the lecture, but let me go through this one more time quickly, and then we'll go through in detail again when we go through the topic for today. Okay, so how to calculate the assortativity index based on node degrees. So given a graph like this, write down the edges in the graph. So the edges are written, you could write them in any direction, any way, but we will follow this convention. So the 2 end vertices of the edges will follow the convention of writing the lower ID vertex first, followed by the higher ID vertex. So we'll write it as for node 1, 1, 2, 1, 4, followed by 1, 5. So for node 1, these are the other end vertices of the edges associated with node 1, and we write them in increasing order. Then for node 2, we have 2, 1 is already covered here because it's undirected, 1, 2 is same as 2, 1. So we don't write 2, 1 again. So we'll write only the higher IDs, node IDs greater than 2, connected with 2. So for node 2, that's going to be only 4. For node 3, 3, 4 and 3, 5 are the 2 edges. Now for node 4, all the edges, the other end vertices are lower ID, which are already captured somewhere above. Similarly for node 5, the other end vertices or lower IDs captured somewhere above. So these are the 6 edges in this graph. So once you write down the edges in this order, you represent a set called X for the first end vertices of those edges. So these vertices are said to be part of the set X, and these vertices are said to be part of the set Y. So basically then you write down the degrees of the end vertices in the set X and set Y. So for node 1, the degree is 3, so you write them for each edge 3, 3, 3. Then node 2, the degree is 2. For node 3, the degree is 2. Again for node 3, the degree is 2. Then for set Y, the end vertices are these. 2 for node 2, the degree is 2. For node 4, the degree is 3. For node 5, the degree is 2. Node 4, again the degree is 3, and so on. So you may notice a vertex may appear in both the set here, X and Y, doesn't matter. So you are just looking at the sequence, and corresponding to those node IDs, write down their node degrees. That's all you have to do. Then what you do is take the average of those x value, the degree values for the set x. So this is the average of these numbers, 3, 3, 3 and all these numbers, 2.5. And this is average for all these values here, which is also 2.5. Now this is just coincidental for this example, it may not be always the same, the average value. So then what you do is do x minus average of x. So the degree values 3 minus 2.5, so that is 0.5. 3 minus 2.5 is 0.5 and so on. Similarly, take average difference of y minus average y. 2 minus 2.5 is negative 0.5. 3 minus 2.5 is 0.5 and so on. Then what you do is square these numbers. So 0.5 square plus 0.5 square plus 0.5 square and so on. So square these numbers and sum them up. That is 1.5. Similarly, square these numbers and sum them up. That is also 1.5. Then you should also take the product of these differences, which is 0.5 times negative 0.5 is negative 0.25. 0.5 times 0.5 0.25. So once you do all these calculations, you plug them in here in this formula. Now this is called the Pearson's correlation coefficient formula. So correlation coefficient basically captures if the x values increase, the y values increase or not. So that's what we want to find out. If one end of the edge has a degree 3, is the other end also having a degree 3, or is degree very far away from 3 or far less than 3? So that's what we are going to find out. That's a similarity. That's a measure of how similar are the end vertices of the edges, and that's what is called Assortativity Index. So that's why you expect you find the differences, product of the differences, and you sum them up, and that's the numerator, the sum of the product of the differences. So the sum of all these numbers, you get negative 0.5 in this case, divided by square root of the sum of the squares. So you have to take a square root of 1.5 and square root of this 1.5. And that's in the denominator, square root of 1.5 times square root of 1.5. So negative 0.5 divided by this square root of 1.5 times square root of 1.5, and that's going to be negative 0.333. So the correlation coefficient or the assortativity index can range from negative 1 to 1. If it is negative, especially negative 0.2 or above or less than that, close to negative 1, we can say the network is disortative in nature. On the other hand, if it is close to positive 1, then we can say the network is more assortative in nature. And if it's close to 0, we can say the network is kind of neither assortative nor disortative. We can say that is neutral. Okay. So we will work with a couple of graph examples today, and we can find out, we can see sometimes the correlation, the assortative index can be close to negative 1 or close to positive 1 in our cases. So this is what we went through last time, and I kind of went through in a nutshell today. So there are videos on this lecture last week, so you can go through them in detail, and we'll start. Any question before we start? We'll start the lecture for today now. Let me save this video.